Okay, so this is 15.3. So let F be some sort of a vector field, so equal to mi nj pk. Then we're going to define the curl of F to be this 3x3 determinant over here. It looks like the definition of cross product, and it's related. So let's take a look at an example. So the example here, find curl for a vector field. So our F is 3x squared y in the I direction, x plus y plus z in the j, 2xz in the k. Okay, so let's find the curl. Okay, so I've written in my definition here with my m function, in this case being 3x squared y, the n being the x plus y plus z, the p being the 2xz. Okay, so it's like doing a cross product. So you take away the I column and I row to give you the I component then, so it's going to be, so taking this away and that away, so covering this and this. So it's going to be then partial y acting on 2x z minus partial z acting on x plus y plus z. That will be in the I direction. Okay, then bring it over here. So then we'll do the j component next, just like in cross product. So just like in the cross product here, we'll have a minus then, so it'll be minus. So then you take away the column j's in, let me go like this. So take away the column j's in and the row. Okay, in the row. And so you'll have partial x acting on 2xz. So partial x acting on 2xz. So you're taking this away. Then there'll be partial z acting on this guy. So minus partial z acting on 3x squared y. This is in the j direction. And then a plus. So in the k direction, so you take this away. So it'll be partial x acting on this guy. So partial x acting on x plus y plus z minus partial y acting on this guy. So partial y acting on 3x squared y. This is in the k direction. Okay, so let's keep going. Okay, so looking at the top guy up here, so let's write down here. So partial y acting on 2x z, well there's no y there, so it'll be 0. Then minus z acting on x plus y plus z, well that's a constant, x with respect to z, so that's a constant be gone, so it'll be just 1 here. So it'll be minus 1 I, and then minus, moving on to this one, partial x respect to 2xz, so just be 2z, and partial z acting on this, there's no z's here, so it'll be 0, and then partial x acting on this guy, derivative of x will be 1, and these are constants will be gone, so it'll just be 1, and then minus partial y acting on this guy, so derivative of y is 1, so it'll be just 3x squared here. Okay, so then we can write this as negative I minus 2z j plus 1 minus 3x squared k. Okay, so let's make an observation, a note here. So note, so my note over here, that when we did the curl, it's another, this guy is another vector field, because that's an I, j, and k component. So note curl of f is another vector field. So when you take the curl of a vector field, it's going to create another vector field. Alright, so let's keep going. Okay, so we're going to make a definition. We're going to call defined as delta to mean partial x respect to I, partial y respect to j, partial z respect to k. We call this a del operator. Okay, so you'll see why in a second. So convention, so we call the del operator across f is another way to denote the curl. Okay, so say we have a vector function, so f equals mi nj pk. Then we're going to define the del operator dotted with f. So just by looking at it, it'd be, if you're going to dot these, you'd be this guy times this, multiplying the I components. So when you multiply these together, then basically this guy is going to operate on m. So it'll be partial m respect to x here. This guy will operate on the n because they're j components. So it'll be partial n respect to y, and dotting these, this guy would operate on the p. So we're going to define our del operator dotted with f this way. So we call our del operator dotted with f the divergence of f. And convention, div of f is another way to denote the divergence. Okay, let's look at an example now. Okay, so let's look at an example. Find the divergence of our vector field. This is the same one as the when we found the curl of the last example. So okay, so let's write down our definition of divergence. Okay, so the partial x guy will be acting on the I component here, so it's going to be 3x squared y. The partial y operator is going to be acting on the I component of the vector function, and the partial z operator acting on the k component, so it'll be dx z. Okay, so keep going with this. So derivative of this guy with respect to x, so it'll be 6xy. Derivative of this guy with respect to y will be 0, 1, 0, so just be 1. And derivative of this guy with respect to z, just be 1 for z, be 2x, let's let it be 2x. So this will be our answer. Note there's no, when you do the divergence, there's no I, j's, and k's anymore. So note here, this is our answer here. I guess yeah, it's fine. So note here, the divergence is no longer a vector field. And what I mean by that is, so a vector field has to have a function in the I, a function in the j, and the function in the k. This doesn't have any I, j's, or k's. I guess I could write this as 6xy plus 2x plus 1. But it doesn't have any I, j's, or k's. It's just a real value function now. Okay, now let's look at theorem 13. Okay, here's theorem 13. So say we have a vector field and assume that the components of the vector field, the m, n, and p functions, have continuous second partials. Then it says, the theorem states that the divergence of the curl of f is 0. Okay, so let's look at the proof of this. Okay, so first note, so I wrote the definition of curl here. So then I just wrote it out using the 2x2 determinants. For example, how I got the I one was, I just covered that, and there's that 2x2 determinant right there. So I got this guy. Then a J1, I just covered the J column. You put a minus sign in front, so that's how I got this guy. And the K1 over here, that's how I got this one over here. Okay, so let's work out these guys. So it'll be this times that. So it'll be partial p respect to y minus partial n respect to z I, then minus partial x operator acting on p minus partial z operator acting on m j, and then this times that, so it'll be partial x operator acting on n minus partial y operator acting on m. This would be in the k direction. Now we're going to take the curl of this and show it 0. So it follows then that the divergence then of our curl, so it's going to be the partial x operator acting on this guy. So the partial x operator will act on this, will distribute and act on this also. So it'll be partial p, let's put the x here, y, and minus second n partial x, partial z. Then the partial y operator will act on this one. So it'll be then minus partial p, partial x, partial x. Then it'll be double minus here, then be plus second derivative respect to x, z, and then our k guy, sorry, our z guy will operate on this. So it'll be then partial n, so it'd be z, square x minus partial, second partial with respect to xy. Okay, so we have to show that this is 0. Let's see. Well, let's take a look here. We're assuming now the m, n, and p have continuous second partials. We're going to use that to our advantage here. Hold on, I just realized I made a few mistakes here. Actually, I need to be careful. So the y operator is acting here, so this should be y here. And it should be y. So I don't know what I was thinking here. And the z operator is acting on this guy, so it should be z, and it should be z here also. So I wasn't quite sure what I was doing there. So it should be x acting on this, and here, y acting here, in here, z acting here, in here. Look at x, x, y, y. Okay, so now it looks good. So now, since they have continuous second partials, the x, y, p1 and the y, p1 will be the same. And then you got one minus and one plus here, so they'll cross off there. And the n's here, you got a zx and an xz. One's positive, one's negative. They'll cross off there also. And the m guy, you got a yz and a zy, so they'll be the same also. One's plus, one's minus, so they can cross off too. So we get 0. So we're done with the theorem. So done.